Have you ever wondered what makes everything move? From sound to light to earthquake? The answer is simple. Waves that carry energy everywhere. Hi, and good day everyone. I'm Christian Tambien, and together with my amazing groupmates, Barry, Mamakos, Del Santos, and Purissima, we're here to uncover how waves carry energy, why some waves are more intense, and how this affects the worlds around us. Let's dive in and explore the power of waves together. And speaking of the power of waves, let's dive into our main topic, which is energy in waves intensity. Before we start, here are the objectives of our report. By the end of this lesson, we should be able to describe superposition of waves, apply the inverse relation between the intensity of waves and distance from the source, and recognize the importance of relating the frequency and wavelength of sound with the motion of the source and the listener. Now let's begin with our first topic, wave intensity. The intensity of wave, also called irradiance in optics, measures how power is delivered per unit area. It describes how the energy of a wave spreads out over a surface. The unit of wave intensity is watt per square meter. So basically, wave intensity, it tells us how strong or powerful a wave is at a certain distance from the source. So the formula for the wave intensity is I equals to P over 4 pi r squared, where I is the intensity and P is for the power and R is for distance from the source. Example, current measures a wave at 5.0 meter with a power of 9.4 watt. What is the intensity of the wave? So first things first, we have to define the given and the unknown. So for the given there, we have the power which is 10.4 watts and the radius or the distance which is 5.0 meter and the unknown is the intensity wave. So for the solution na to, so we have to use the intensity of wave formula which is intensity is equals to P over 4 pi r squared. So, is-substitute lang nato ang atong given sa atong formula. So, we have 9.4 over 4 pi times 5.0 squared. So, next thing na atong himuon is squared na to ang 5.0. So, mahimo siyang 25. So, we have 9.4 over 4 pi times 25. Next thing na tong himuon kay i-times na to ang 4 pi sa 25. So, we have 9.4 over 100 pi. So next is we have to calculate the 100 pi. So, the equivalent for 100 pi is 314.1592. So, for our solution, so mahimo na to siya ang 9.4 over 314.1592. So, kung i-divide na to 9.4 divided by 314, so, may mo na siyang 0.0299 watts per square meter. Or, pwede po na scientific notation na to which is 3.0 times 10 to the power of negative 2 which is dili na to kalimtan ng unit sa intensity of wave which is watt per square meter. So we can conclude that therefore the wave intensity at 5.0 meter from the source is approximately 3.0 times 10 to the power of negative 2 watt per square meter. Another example, Lei found out that the intensity of the wave is 13 watt per square meter with a power of 2.6 watt. What is the distance of the wave from the source? So first things first, we have to define the given and the unknown. So the given there is the power which is 2.6 watt and the intensity is 13.4 watt per square meter. So the unknown there is the distance from the source which is the R. So for the formula, so since distance pa na itong pangitaon, gamito na to ang formula sa intensity of the wave niya. I-rearrange na to para sa distance. So kung ma-rearrange na to tong formula sa intensity of the wave, so mahimo na siyang R equals to square root of P over 4 pi I which is the intensity. So for the solution, we have to use the rearrange formula for the distance. So ang formula tong gamitos kay R or distance equals to square root of P over 4 pi L. So, substitute lang nato ang given sa ato ang formula. So, mahimo na siyang R is equals to square root of 2.6 over 4 pi times 13.4. So, first na tong i-times kaya ang 4 pi o ang 13.4. So, i-times na to ang 4 pi sa 13.4, mahimong 167.38937. So, mahimo ng square root of 2.6 over 168.38937. So, i-divide na tong 2.6 sa 168.38937. So, mahimo na siyang square root of 0.01544. So, square root na to tong 0.01544. So, mahimo na siya og 0.12 meter. So, mao na ito ang final answer. So, we conclude that therefore the wave is approximately 0.12 meters away from the source.
Inverse square law. The inverse square law explains that the intensity of a sound or any wave decreases as the distance from the source increases. This happens because as you move farther from the source, the wave's energy spreads out over a larger area. So, the same amount of energy is distributed more thinly, making the sound weaker. The relationship between intensity and distance is shown by this formula. I sub 1 over I sub 2 equals R sub 2 squared over R sub 1 squared. Here, I sub 1 and I sub 2 represent the intensities of the wave at two different distances, and R sub 1 and R sub 2 represent those distances from the source. This means intensity is inversely proportional to the square of the distance. So if you double the distance from the source, the intensity becomes 4 times smaller. Let's solve an example to understand this better. If the sound intensity 3.0 meters from a sound source is 4.0 times 10 to the negative 6 watts per square meter, what will be the intensity at 1.5 meters? We are given R sub 1 equals 3 meters, I sub 1 equals 4.0 times 10 to the negative 6 watts per square meter, R sub 2 equals 1.5 meters, so we need to find I sub 2. We start with the formula I sub 2 equals I sub 1 multiplied by the square of R sub 1 over R sub 2. Now, substitute the given values. I sub 2 equals 4.0 times 10 to the negative 6 multiplied by 3 divided by 1.5 squared. 3 divided by 1.5 equals 2. Then 2 squared equals 4. Multiply 4.0 times 10 to the negative 6 by 4, and the answer is 1.6 times 10 to the negative 5 watts per square meter. This means the sound intensity increases when we move closer to the source. From 3 meters to 1.5 meters, it becomes 4 times stronger. Now, for the second example. We use the same given data, but this time, the new distance is 12 meters. We again use the same formula, I sub 2 equals I sub 1 multiplied by the square of R sub 1 over R sub 2. Substitute the values. I sub 2 equals 4.0 times 10 to the negative 6 multiplied by 3 divided by 12 squared. 3 divided by 12 equals 0.25. Then, 0.25 squared equals 0.0625. Multiply 4.0 times 10 to the negative 6 by 0.0625, and we get 2.5 times 10 to the negative 7 watts per square meter. So, at 12 meters, the sound intensity decreases to 2.5 times 10 to the negative 7 watts per square meter. This clearly proves the inverse square law. As distance increases, the intensity of the wave decreases rapidly because the energy spreads out over a larger area. That's why, when we walk away from a loudspeaker, the sound becomes softer. The wave's power stays the same, but its intensity gets weaker with distance.
Superposition of wave is the phenomenon that occurs when two or more waves meet at the same point in a medium, and their displacements combine such that the total displacement at the point is equal to the sum of individual wave displacement.
And now, let's move on to wave interference. So, wave interference happens when two waves meet while traveling in the same medium. The shape of the wave changes depending on how the two waves combine. If two waves move toward each other and meet, their effects can add up, making a bigger wave with a double amplitude. This is called constructive interference.
There are two main types of superposition. The first one is constructive interference. This happens when two waves meet in phase, meaning their crest and throws align perfectly. When this happens, their amplitudes add together, forming a wave with a greater amplitude. In other words, a stronger or louder wave. The formula for this is y equals a sub 1 plus a sub 2. For example, imagine two speakers playing the same sound. If one wave has an amplitude of 2 centimeters and the other has 3 centimeters, then they combine to form a wave with an amplitude of 5 centimeters. This means the sound becomes louder because the waves reinforce each other. You can visualize this as two waves rising and falling together, merging into one taller wave. The second type is destructive interference. This occurs when two waves meet out of phase, meaning the crest of one wave overlaps with the throw of another. Their amplitudes subtract, producing a wave with smaller or even zero amplitude. The formula for this is y equals a sub 1 minus a sub 2. A good example of this is how noise-canceling headphones work. They produce a sound wave that's the opposite of the external noise. So if one wave has an amplitude of 4 centimeters and the other has 4 centimeters in the opposite direction, the result will be y equals 4 minus 4 equals 0. The waves cancel out completely, creating silence. You can picture this as a crest and throw meeting and flattening out into a straight line.
Standing waves. A standing wave is a pattern formed when two identical waves move in opposite directions and interfere with each other. Unlike a traveling wave that moves through the medium, a standing wave appears to stand still. That's why it's called a standing wave. This wave pattern is created by the superposition of the incident wave and the reflected wave. It is a result of alternating constructive and destructive interference. In a standing wave, there are two important parts: nodes and antinodes. A node is a point that stays completely still. It has zero displacement. An antinode is the opposite. It's a point that vibrates with maximum displacement. The distance between two consecutive nodes or two consecutive antinodes is equals to one half of a wavelength, or lambda over 2. Formation of the standing wave. So a standing wave forms when two waves meet and overlap. The formula is y is equals to 2a sine kx cos omega t, shows sine kx is the wave shape and the cos omega t is vibration over time. An example of a standing wave. So considering a standing wave with a wavelength on a string having an indefinite length as shown in the figure below. In terms of 1, find the position x of the nodes and the antinodes. A standing wave is formed when two waves of the same size move in opposite directions and interfere with each other. This causes points that don't move, called nodes, and points that move the most, called antinodes. For the solution, we start with the equation of a standing wave. Yxt equals 2a sine kx cos omega t. This shows how the wave moves up, down over time. To find the nodes, we look for the points that never move. That happens when sine kx is equals to 0, because that makes y equals 0. Solving this gives x equals n times wavelength over 2, where n is equals to 0, 1, 2, 3, and so on. So the nodes are found at x is equals 0, wavelength over 2, wavelength, 3 wavelength over 2. These are the points on the string that stay still. Next, to find the antinodes, we look for where the vibration is the greatest.
This happens when sin kx is equals to 1 or negative 1. Solving this gives x equals 2n plus 1 times wavelength over 4, where n is equals to 0, 1, 2, 3, and so on. So the antinodes are at x is equals to wavelength over 4, 3 wavelength over 4, 5 wavelength over 4. These are the points that move the most. In short, nodes don't move, and antinodes vibrate the most, forming the pattern of a standing wave on the string.
Sound intensity. Sound intensity is the amount of sound energy passing through a unit area per unit time, perpendicular to the direction of the sound wave. So for the formula for the sound intensity is I equals to P over A, where I is the intensity, P is the power of the sound wave, and A is the area perpendicular to the wave's direction. So the unit for the sound intensity is wave per square meter. So example, a speaker emits a sound wave with a power of 8 watt. The sound spreads uniformly over an area of 16 meters squared. Find the intensity of the sound at the surface. So first thing, we have to find the given and the unknown. So the given there is the power, which is 18 watt, and the area, which is 16 meters squared. So the unknown there is the intensity of the sound at the surface. So we have to use the formula for the intensity, which is P over 8. So we have to substitute the value to our formula, which is the P over 8. So, substitute lang. So, mahimo na siya og 8 over 16. So, just divide 8 sa 16. So, mahimo ng 0.5 watt per square meter. So, we conclude that therefore, the intensity of sound is 0.5 watt per square meter. Threshold of hearing. The human ear can detect sound starting from an intensity of 1 times 10 to the power of negative 12 watt per square meter, known as the threshold of hearing. Because sound intensity can vary widely, sound intensity levels are measured relatively to this threshold using decibels. The relationship is expressed as beta equals to 10 dB log times I over I sub 0, where I is the sound intensity in watt per square meter, and I sub 0 is equals to 1 times 10 to the power of negative 12 watt per square meter. Reference intensity threshold of hearing. Example, a motorcycle engine produces a sound with an intensity of 2 times 10 to the power of negative 5 watt per square meter. Find the sound intensity level in decibels. So first thing, we have to find the given and the unknown. So the given there is the intensity, which is 2 times 10 to the power of negative 5 watt per square meter. So, and the threshold of hearing, which is 1 times 10 to the power of negative 12 watt per square meter. So, constant na siya. So, an unknown there is the sound intensity level in decibel. So, we have to use the formula for sound intensity level in decibel. So, ang formula niya is sound intensity level in decibels is equals to 10 log times intensity over threshold of hearing. So, substitute lang nato ang given sa ato ang formula. So, mahimo siyang 10 log times 2 times 10 to the power of negative 5 over 1 times 10 to the power of negative 12. So, first thing na tong himuon is i-divide na to ang 2 times 10 to the power of negative 5 sa 1 times 10 to the power of negative 12. So, mahimo na siyang 10 log times 2 times 10 to the power of negative 7. So, next na tong himuon is mogamit ang product rule sa logarithmic. So, kung mag-multiply ka og duha ka number sa isa ka logarithmic, pwede nimo siyang i-rewrite na i-plus nimo siya sa two separate logarithm pero same ang base. So mahimo na siya og 10 log 2 plus log 10 to the power of negative 7. So mahimo na to siya og 10 times 0.3 plus 7. So i-plus na to ang 0.3 sa 7. So, mahimo na siya og 7.3. So, mahimo ng 10 times 7.3. So, ang answer na to, ana, is 73 decibels. So, Pa-conclude therefore, the motorcycle sound intensity level is 73 decibels, which means it is about 10 million times more intense than the threshold of hearing. Here in the diagram, we can see the various sound intensity levels, ranging from the threshold of hearing at the bottom to the threshold of pain at the top. At the bottom, around 0 decibel, we have the threshold of hearing. This is the faintest sound that the human ear can detect, such as the sound of quiet room or breathing. As we move up to the scale, the decibel level increases, meaning the sound becomes louder. For example, around 60 to 70 decibels, we hear sounds like conversation or background music. Around 90 to 100 decibels, we have buses or trains, which is already quite loud. Beyond 120 decibels, like a car horn or pneumatic drill, the sounds can cause pain or ear damage if exposed for too long. Finally, at around 130 decibels, we reach the threshold of pain, which is the limit of what our ears can tolerate without injury. This chart shows how sound intensity increases from very soft sounds to extremely loud and harmful ones. It helps us understand why protecting our ears from high decibels sound is important.
The Doppler effect is the change in observed frequency or pitch of a sound when either the sound source or the listener is moving. For example, when an ambulance passes by, you'll notice the siren sounds higher as it approaches and lower as it moves away. This is because the sound waves are compressed when a source moves toward you and stretched when it moves away. The relationship between the actual and observed frequency is given by the formula f prime equals f times the quantity of v plus or minus v sub o over the quantity of v plus or minus v sub s, where f prime is the observed frequency, f is the actual frequency, v is the speed of sound, v sub o is the speed of the observer, and v sub s is the speed of the source. This formula helps us calculate how much the frequency changes depending on whether the sound source and the listener are moving toward or away from each other. So how does it work? When a source moves towards the observer, the sound waves are compressed, meaning the frequency and pitch become higher. When a source moves away, the waves are stretched, which lower the frequency and makes the sound deeper or lower in pitch. This is why a moving vehicle sounds different before and after it passes by. The Doppler effect also affects loudness. As the source moves closer, the sound becomes louder because the waves are packed closer together and reach your ears more frequently. But as it moves away, the sound becomes softer because the waves spread out and lose intensity over the distance.